Okay, so this is going to be lesson 2-2, and we are going to be solving one-step equations. So first, just a few vocab things. What does it mean to solve an equation? So when you solve an equation, basically you'll have an equation where maybe you have an unknown, and you are going to be giving an actual value to that unknown. So you'll be finding out the values of all unknown variables in your equation. So, for example, if I have something like x plus 7 equals 13, if I were to solve this equation, I would want to find this value of x as an actual number. And so to do that for this case, we would simply subtract 7 from both sides of the equation. And so we would get x plus 0, so just x, equals 13 minus 7, so that would be 6. And so x equals 6. This would be an example of solving an equation. When we talk about solving an equation, we are taking an equation with a unknown variable and making it known, finding out what the value of the variable is. So this would be an example of solving an equation. So the other thing would be a idea of equivalent equations. What makes two equations equivalent? And really, we already have an example of equivalent equations. This equation here and this equation here are equivalent. They are in a way saying the same thing. We can get from if I start out with an equation, let's say x plus 6 equals 13 cubed. This is an equation. An equation that would be equivalent to this would be any equation that we could use operations to get back to this original equation with. So, for example, if I were to add 2 to both sides of this equation, x plus 6 plus 2 equals 13 cubed plus 2. These equations are equivalent. There's a number of ways that you can test and verify their equivalent. One is you could show that you can get from this equation to this equation by just subtracting 2, obviously. The other one, and probably the more sensible one in a lot of ways, is the value of x will be the same in our equivalent equations. Everything will be the same as far as the end result. And so equivalent equations are ones in which you can get between them by without changing the value of any of your variables. So I think that is probably the most straightforward definition of equivalent equations. It would be two equations that have the same value for each variable, and you can get from one to the other using things like adding to both sides, dividing the same number to both sides, and we'll be talking more in depth about how to go about manipulating equations to get from one equation to a more useful equation that is equivalent to the previous one. So just kind of some ideas to think about as we get into it. And as we already kind of know, there's this idea of an addition property of equality, or additive property of equivalence. So if I have something like x plus 2 equals 7, excuse me, we are completely free to add 10 to both sides of this. Not sure why we would, but we can. So this would leave us x plus 12 equals 17. There is nothing that changes from doing this. These two equations are equivalent equations. Okay? Let's see here. I think maybe another important thing to remember is, actually, let me make 100% sure. So we also, in the book, we talk about the subtractive property of equality, But I think it's really important to kind of think about um, really subtraction isn't really very much different from addition in a lot of ways. Of course, there are some differences. Addition is commutative, subtraction is non-commutative, but really they're a lot alike. And if I can add 10 to both sides, then I can add. So let's see. Plus 2. I'll write this out again. 7. If I can add 10 to both sides, if I can add anything I want to both sides, I can add negative 10 to both sides. And so this would give me x minus 8 and negative 3. Now, these two equations are going to be equivalent equations. And notice here, even though we were kind of using the same idea of adding, this really is subtracting. So what I'm kind of trying to say here is there is something called the subtractive property of equality, but that property, it's really just the additive property kind of in disguise, because we can add anything we want as long as we add it to both sides, and so we can add negative numbers, and so really that's where we get this idea that we can subtract from both sides. It's probably shorter to just omit this addition, saying add negative 10, and simpler to say subtract 10. But I think it's kind of neat to know that really this is our old friend, the additive property, just kind of under a different name here. So hopefully that makes sense. If there's any confusion from that, please let me know. But let's move on. Okay, so then we have this notion of and let me clear my board really quick. So then we have this notion of the multiplicative property of equality. So the multiplicative property of equality has kind of a similar idea. So if I say x plus 2 equals y times 7. This is an equation. And really, even if we can't solve for x or y, it doesn't mean we can't think about this equation, think about different ways we can manipulate it. So let's think about if we take one side of this equation. We can multiply one side of this equation by 3 as long as we multiply the other side of the equation by 3. So we are always free to multiply both sides of the equation by the same number. Okay? And really, when it comes down to it, the big thing that will be seen a lot with this is if you do something to one side of an equation, you have to do the exact same thing to the other side of the equation. So if you multiply one side of the equation by 3, you got to multiply the other side of the equation by 3, and that will give you that will keep the equation true. It will not mess with the value of the equation. You'll get an equivalent equation as long as whatever you do to one side, you do to the other. Okay. And so, following the trend of addition, then subtraction, multiplication, I think we might be able to guess what's coming next. Let's see. Maybe they don't. Oh. Oops, my bad. So yeah, it was coming up. We have the division property of equivalence, and again, I kind of like showing you that it's not anything new. So we have this x plus 2 equals y times 7. Now let's say instead of because I just want to use multiplication. So why don't I just multiply both of these sides by a third? This would be the same as if I divided both sides by 3, and so really this division property, it's nothing new. It's what we had before. It's our good old multiplication property. And make this over 3. So that is the different properties of equivalence. And we can use these to solve different equations. So if we want to have something like, let's see here, if I have an equation like x minus 20 equals 7. I can use my additive property of equivalence to solve this equation, get x on one side, and know what the value of x is through that. So all I would do here is I'd want to use the additive property of equality. I would add 20 to both sides, because I want to get x on its own. So what would that leave me with? I would get x equals, this would be 0, so I wouldn't have to worry about this anymore, and it would be 27. Okay? So that would be an example of using the additive property of equivalence to solve an equation. And naturally, we will be typically seeing this if we have something like negative values, like x minus 1 equals 2. We would add 1 to both sides to get rid of this negative 1 over with our x, because we really want to get x on its own. So we get x equals 3 for this. Okay? And so I think it's kind of important to work through a few of these, but hopefully this is kind of making sense why we're using the additive property, why we're adding, and really the driving force behind all this should be just to get x isolated. So with that being said, kind of the similar one is going to be the subtractive property. And so really it's almost the same thing, just now instead of having a minus, we now have a plus. So x plus 5 equals 8. So if we have this, what would we do? Well, we would subtract both sides, or 5 from both sides. And so we would get x equals 8 minus 5 is 3. X equals 3. Now, I kind of sometimes like to check myself just because, it's very possible that you make a little mistake. So on these, I would definitely encourage you, especially for tests or if ever you're working on something important that you really want to know you did things right, just take this x equals 3 and plug it back in for here, because now we know x equals 3, and so we have 3 plus 5, and 3 plus 5 does equal 8, so this is true, this works, and so that's good. Just to be sure you know what to look for, if we messed this up and got x equals 2, what would have happened? Well, we would have gotten, instead of this 3, we would have gotten a 2 here, right? And what's 2 plus 5? It's 7. So this statement is now wrong, and that would tell us, oops, we solved through and got the wrong x. We better go back and look what, look if we made any mistakes. So it's always a good idea to go through and check yourself on these, because you can really typically find out if you made a mistake if you just put an extra a few seconds into the solving the problem. With that being said, let's go on to solving some multiplicative and some equations with multiplication and division. So if I say that 7x equals 10, so this I would obviously be dividing because I want to get x on its own, and I would want to divide both sides by 7. So this 7 and this 7 would cancel, and so I'd be left with x equals 10 over 7. And really, I know we can take and divide this out and everything, but for the most part in class, I really am completely happy if you can take this number and turn it into a mixed fraction. So if you can just get this to me in a mixed fraction, I will be happy. If you can get it in its most simplest form, if that makes sense. So I would want this to be, how do we get this into a mixed fraction? We would say, well, 10 goes into 7 one time, so we'd have 1. Then after 10 goes into 7 one time, we'd have 3 left over, so 1 and 3/7. If you can get me it in this type of form, I would be completely happy with that. I don't want to see things like 10 over 7. I don't want improper fractions, and I also wouldn't be too happy if you gave me like 2 over 4. Just go the extra, do the extra little bit of work. Oh, that didn't look like an error at all. Do the extra little bit of work and get me 1/2. That's all I ask for. I'll specify if I want it in decimal, but fraction will be fine, and really that will help with making, you won't have to put as much time into it. You can work more on solving the equations, which is what we're really wanting to be doing right now, and less time in doing your division, your long division, which, while it's a very important thing to be able to do, I don't want you to put that much time into it right now, because I kind of feel like at this point you probably know how to do long division. So stressing this, just kind of worry about the being able to write it out in a somewhat easy, compact version. With that being said, we can do as many of these as we want with the using division. It's just whenever you see something like 5x, whenever something is being multiplied by x, we want to get rid of this thing that we're multiplying by our x, because we want x alone on one side. So we simply divide both sides by 5, and so we get x equals 6 over 5. So that would be 1 1/5. Okay, and so really this is pretty straightforward if you think about it. It's not very nasty stuff. And similarly, we have this idea of solving using the multiplicative property. So if I have something like x over 5 equals 10, here I would use multiplication. I would multiply both sides by something. And I want to get rid of this 5 here, so I would just multiply both sides through by 5. Okay. So this 5 is going to cancel with this 5, and so I'll get x equals 50. Now, maybe this is pretty straightforward and easy. I think the thing that will trip people up the most is picking which one to use. So if I have x plus 10 equals 6, x times 10 equals 6, x divided by 10 equals 6, and x minus 10 equals 6. Which will I use in each of these cases? Which, will I add 10 to both sides? Will I divide 10 from both sides? And there's a few different ways you can approach that. I think it's important to know what our end game is. We need to kind of keep in mind, always keep your eye on the prize. And in all of these cases, we have the same end game. We want to get x alone on one side of the equation. And so if you keep that in mind and you make a mistake, so if I take this equation here and I make a mistake, and I say, well, I'm going to multiply both sides by 10. And so I do 10 times x plus 10. Always make sure you keep your parentheses, equals 6 times 10, so 60. So if I do this, then I can distribute my 10 through, and I get 10x plus 100 equals 60. And I mean, it's the type of thing where I think it's very clear that we have taken this equation and we have not gone any way of getting x alone on one side. We, if anything, have made this equation more complicated. So the thing is with this is not a wrong statement. It's not something like this is now wrong. It's just not helpful. So as long as you know that you need to get x on its own, you can make a mistake and accidentally multiply when you shouldn't have, and you won't get to the wrong answer. You'll just get a more nasty equation. Now you'll have more work to do. So really you can be like, oh, this looks like more work now. I don't really feel like doing more work now. I'm going to go back to here. And so, you can kind of see that as long as at the end, if you finish with x on one side, it doesn't matter the path you take. So don't be worried that you'll do the wrong thing and then your question will be wrong and you'll have no way of knowing. As long as you follow the idea of what you do with one side of the equation, you do to the other, you will never get the wrong answer if you finish up with x on one side alone. The only thing you might do is give yourself a bit more work to do, and a lot of times just saying, I don't feel like doing that, I'm gonna go back to square one. I'm not worrying about that, so I'm gonna go back to square one. What else can I try to do? And I think with this one, it's not too difficult to see what we got to do. So we have x plus 10 equals 6. We want to get rid of this 10, and so what are we doing? We are adding this 10. So if we want to get rid of it, all we have to do is minus 10. Minus 10. Or plus negative 10 if you'd like to use the additive property. I'm fine with either way that you want to look at it. Same thing. So we have x plus 10 minus 10. That equals x. And then what's 6 minus 10? That's going to be negative 4. So x equals negative 4. And again, sometimes it's nice to check ourselves. So if we take this equation and we bring it down and we write it out, we can say negative 4 plus 10 equals 6. And that's correct, right? Negative 4 plus 10 equals 10 minus 4 equals 6. So we were able to solve this equation. So give ourselves a little check mark, give ourselves a pat on the back, and we'll just write out x equals negative 4 here. Okay, so 1 second. Oh wow, that doesn't look right at all. Okay, I'm just going to start a fresh slate. So, I'm gonna grab my pen, make that 15. Sorry about that. And so we have everything pretty much, we have our first one solved. So that was x plus 10 equals 6. Wait, yeah, x plus 10 equals 6. And we have that one solved. And we know that x equals negative 4. Now we have, what about x times 10 equals 6? So here, we want to get rid of this 10. But notice we're not, adding 10 anymore, so we're going to want to do something different. And so how would you get rid of this times 10? Well, I think it's fairly clear that we would want to just divide both sides of this by 10. It's 10, we'll cancel with that 10, so very good. And we're left with x equals 6 over 10. Now, again, this is something that I might not like this too much because I'd like it in its most reduced form, and so I would appreciate it if your numerator and your denominator share no common divisors greater than 1. So 3 and 5. There. So here we go. 3 and 5 are relatively prime, and that's what I would like. I would like them to not have any common denominator. I guess the greatest common denominator should always be 1 for my fractions. They should be in their most simple form. I'm not going to take off too many, but make sure you get it kind of as far down as you can. Reduce your fractions as much as you can. So with that being said, this is what my value of x will be. Okay? I hope that makes sense. If it doesn't, just feel free to ask questions either in the comments or when you come into class. So, but we have this now. Good. And we know that x equals 3/5. And we can even check ourselves really quick. We have x times 10 equals 6. 3 over 5 times 10 equals 6. A lot of ways that we can look through this. Really, I would just look at that 5, look at that 10. 10 is 2 times 5, so I'd cancel that out and get 1 and 2. 3 divided by 1 is 3, so We have 3, then times 2. So we're good. So that's correct. Now we have x minus 10 equals 6. So what can we do here? How are we going to solve for x with this one? Well, all we have to do is add 10 to both sides. And so we get x equals 16. That one is pretty straightforward. We have x isolated on one side, and we just had to get rid of that 10. And so it was very close to the solving it with the x plus 10. And we can check ourselves. It's always a good idea to go through and just make sure you did things right. And that looks good to me. 16 minus 10 is 6. So I'm good on that one. X equals 16. Okay, so our last one is going to be x divided by 10 equals 6. And so we want to get rid of this 10, and so all we're going to do is multiply both sides of this equation by 10. 10's cancel over here, and we're left with x equals 60. So that seems like that value makes sense. Let's really quick go through, plug it in. We have 60 divided by 10 equals 6, and that's obviously what we would get. We would cancel that out, cancel this. That's not really how it would look. The 10 wouldn't cancel the 0, but we would have where just to show you how this would probably end up working. 60 over 10. Well, I know you can write 60 as 6 times 10, and you can write 10 as 1 times 10. And obviously this would then cancel. I felt a little silly saying 0 canceled with 10, so that's where this is coming from. Hopefully that makes sense. So with that being said, these are different ways that we can approach and solve one-step equations, which are really just equations that require just one operation to go from the equation to the solved form where we have x. So next time we will talk about solving equations with 2 or more steps, and those will be pretty much like this, just with a little bit more work involved.